Now see here, today I will discuss the examples on Euclidean angle and Cayley-Killing parameters. Examples with usual notation, so that cos of phi by 2 is equal to cos of phi plus psi by 2 into cos of theta by 2. This example is solved in example 9. However, we will attempt this problem by using the relation between Euclidean angle and Cayley-Killing parameter. We know the Q matrix alpha, beta, gamma, delta in terms of Euclidean angle is given by Q is equal to alpha, beta, gamma, delta e raised to I by 2 psi plus theta phi cos of theta by 2 I e raised to I by 2 psi minus phi sin of theta by 2 I e raised to I by 2 phi minus psi sin of theta by 2 e raised to minus I by 2 psi plus theta phi cos of theta by 2, where alpha, beta, gamma, delta are complex Killing parameters, so that alpha dash is equal to delta, beta dash is equal to minus gamma. This is the matrix of rotation which describes the orientation of the rigid body with one point fixed. Let this matrix be equivalent to the matrix B adjoined by rotating the coordinate axis through an angle phi about an axis with the same origin. Then the matrix B is given by B is equal to cos chi sin chi 0 minus sin chi cos chi 0 0 0 1, or B is equal to 1 0 0 0 cos chi sin chi 0 minus sin chi cos chi. Equation 2. Then the Q matrix in complex two-dimensional plane corresponding to the matrix B is similarly obtained in the form Q chi is equal to e raised to I chi by 2 0 0 e raised to minus I chi by 2, or Q chi is equal to cos of chi by 2 I sin of chi by 2 I sin of chi by 2 cos of chi by 2. From equation 1 we have alpha is equal to e theta e0 plus I e3 is equal to e raised to I by 2 psi plus theta phi cos of theta by 2. Delta e raised to e0 minus I e3 is equal to e raised to minus I by 2 psi plus theta phi cos of theta by 2. Beta is equal to epsilon e2 plus I e1 is equal to I e raised to I by 2 psi minus phi sin of theta by 2. Gamma is equal to minus e2 plus I e1 is equal to I e raised to minus I by 2 psi minus phi sin of theta by 2. Solving this equation, we find e0 is equal to alpha plus delta divided by 2 is equal to cos of theta by 2 cos of phi plus psi by 2. E1 is equal to minus I by 2 beta plus psi sine of theta by 2 cos of psi minus phi divided by 2. E2 is equal to beta minus psi divided by 2 minus sine of theta by 2 sine of psi minus theta phi by 2. E3 is equal to alpha minus delta divided by 2 cos of theta by 2 sine of phi plus psi divided by 2. We see that trace of q is equal to alpha plus delta is equal to 2 cos of theta by 2 cos of phi plus psi by 2. Similarly, from equation 3 we have trace of qx is equal to 2 cos of chi by 2. Since trace is invariant, therefore from 6th and 7th we have cos of chi by 2 is equal to cos of phi plus psi divided by 2 cos of theta by 2. Now see here next example, find a real matrix of orthogonal transformation in three-dimensional space corresponding to the unitary matrix q is equal to cos of theta by 2 I sin of theta by 2 I sin of theta by 2 cos of theta by 2 in two-dimensional complex plane. Solution: to find the matrix of orthogonal transformation in three-dimensional space corresponding to the matrix q is equal to cos of theta by 2 I sin of theta by 2 I sin of theta by 2 cos of theta by 2 in two-dimensional complex plane. Let P be a required matrix operator in a specified UP complex coordinate system in a particular form. P is equal to z x minus I by x plus I by minus z. We notice that the matrix P is trace free and is self-adjoint. P is equal to P dash and x, y, z are real quantities taken as coordinates of a point in a space. Suppose the matrix P is transformed to the matrix P dash by means of the unitary matrix Q in the following way: P dash is equal to Q P P Q dash, where Q dash is the complex transposed conjugate of Q. Q dash is equal to Q transpose of star, called the adjoint of Q. Since Q is unitary, from the unitary property of Q, we have Q dash is equal to I. This implies that adjoint of Q is same as its inverse. Q inverse is equal to Q dash is equal to adjoint of Q. Therefore, equation 3 becomes P dash is equal to Q P Q inverse. This is the similarity transformation of P. Using under similar transformation, we know that the trace free and self-adjoint property of the matrix are invariant. Since P is self-adjoint and trace-free, therefore P dash must be likewise self-adjoint and trace-free. Thus, P dash can have the form P dash is equal to z dash x dash minus I y dash x dash plus I y dash minus z dash, where x dash y dash z dash are to be determined. Let us define x minus iy is equal to x minus, x plus iy is equal to x plus. Therefore equation 5 with the help of equation 1 and gives this is expression and required a solution.